Salutations, everyone. So we are nearing the end of our course, as this is 28 section of 30 sections. So we will have two more sessions on. Sorry, I said section. I meant session. Two more sessions on this one topic, mathematical induction, and then the last session is our final. And I will say more about the final on the webpage. You will see more there. I want to include a quiz of this particular topic, but we don't really have time anymore. So the quiz will be part of the final. The other questions of the final will all be in the same fashion, very similar to some of the quizzes you have gotten, and I will make very explicit which quizzes we are talking about, and then so you have to focus on those quizzes, the reviews for these quizzes, and the solutions for these quizzes. That's for the final. With the one exception, this 5.1, because we won't have time to do a quiz in the regular. There's not much time left anymore. Okay, so what is this topic? Mathematical induction, and this is about proofs. We talked a lot about proofs. I don't know your reaction to this. Many of you might not be very happy with this topic or don't like it that much, but it is very, very much parts and parcel of mathematics. And what mathematicians also, that's the reason that mathematics is accepted, why it's as the scientific, the epitome of scientific truth, is because mathematicians are forced to prove everything that they claim. So every statement that we make has been verified, has been proven. And so I'm a practicing researcher. I write research papers all the time. You can go at my webpage and look at them to see how they look like. And if you just click on it, you are not going to be able to understand anything, because there's still a long step from discrete math to the stuff that I do. But what you will see is that a lot of the content of this thing is, if you just measure the amount of text, you see perhaps 70% of the text is in something that called proof, in sections that are called proofs. So proofs are really the core of mathematics, of mathematical writing, of mathematical research. For you, of course, for students, often proofs are secondary. You just hope that somebody did this correctly, and you rely, you trust that these proofs are there. And so in almost every other course of mathematics that you take, you don't bother about actual proofs. But this is a course about proofs in part, and therefore we have to talk a little bit about it. And we have seen already, I remind you of some of the techniques we had. We had direct proofs. That was proofs when we had to prove some implication, so P then Q, and the direct proof was just you assume P and then develop Q from it. But then we also had seen proofs by contradiction, proofs by contraposition. I'm repeating these for your benefit, because these are things that will come up in the final as well, right? The proof by contraposition was a proof where you actually have this implication, but instead you prove the contrapositive. You assume that a conclusion is false, and then you show that therefore also the premise must be false. But there was something a little bit even more strange, perhaps. So this is contraposition, and this is proof by contradiction. And that is where you say, okay, assume this is not true. Assume that P then Q is not true. And then you get absurdity, something that doesn't make sense out of it. And therefore, assuming that it was not true led to a weird conclusion, and therefore we shouldn't have done that. We should not have assumed it was false, so we should have assumed it was true. Therefore, we've proven that it is true. Okay, these are the proofs we have available. Proofs, go look them up, review them. But the one that I'm now going to talk about is a little bit weirder in some sense, but it is a very powerful proof, and it is used a lot in mathematics. And also many of the things that we claimed in the text can be proven by mathematical induction, and in discrete math 2 you will actually do a couple of those things. In fact, we will also prove some of the results that we have stated before without proof. We will now prove them as well using mathematical induction. So you'll see some of the results that we used involve this type of proofs, but many other things can be done with it. So what is the idea here? The book, for one thing, illustrates this by saying, okay, suppose you're trying to go up a ladder. Okay, so this is my drawing of a ladder. I'm very bad at drawing, so don't make fun of me. Okay, now this ladder goes on forever, or at least is very long. Okay, and the question is, can we walk on the ladder? Now, there's perhaps, if you pose it that way, that's what the book does. It's kind of a little bit silly question, but imagine you are designing a robot, a robotic device, and you want it to be able to climb up a ladder, and for instance, at some point your robot has to carry out a task, and the task involves climbing up a ladder of 20 steps to reach the next level. Right? This is something that you might want to do. You might want to do this in real life, or you might want to do this in a game where you design the robot or whatever character you want to go up a ladder. So what are the things that you need to do? How do you program this? You're going to make a program for it to walk up 5 steps, and then you make a new program to make him walk up 6 steps, and then another program to make him walk 17 steps. No, you're not going to do that, right? What you're doing is saying, okay, if I can make the robot, if he stands on 1 step, and I design a program, or I design a protocol for him to move up 1 step. Okay, so what I'm going to do is make robot go up 1 step. That seems to solve the problem. If I can do this, okay, if he has to go up, let's say 5 steps, then I make him go up 1 step, and then the second step, and then I do it again and again and again, and after 5 times he's where I want him to be. Yes, except for perhaps so here's my robot, right? Okay, I don't know how to draw a robot, so my robot looks like this, okay, and he has like wheels like that, okay. The first thing the robot has to do is find the ladder and actually go up the first step. Okay, so I need to do something else. I have to make sure that he gets to the ladder. So gets on the first step. Let's combine finding the ladder and getting on the first step. Because if he's standing there somewhere in the room, I can tell him, okay, go up 1 step, and he says, I'm not on a step. What do you want me to do? I'm not on a step. I don't know what to do. I don't want to do. And he goes like yeah, you know, starts fulminating and so on. So no. So you have to tell him first, okay, Mr. Robot, please go to the ladder, and I'm telling you, there's a different, this procedure is something special, and this is the first step you're going to do is get onto the first step of the ladder. Okay, that might be a different programming that is required. It's a bit more complicated because he has to find the ladder, and then he has to determine where is the first step, because ladders sometimes, while the distance between steps is always the same, sometimes the first step is a bit lower or a bit higher depending on the type of ladder. So the robot is facing a special problem here to just get on the ladder. But once he's on the ladder, now you make the rest of this program. You tell him now, okay, run this program 5 times, and it goes up, and he's up on the, well, I guess 6th step. Then if you do it 5 times, you have to count it correctly, right? But so that's the point here. There are 2 different things that needs to be done, and in mathematics, although this is perhaps in robotica, this might be difficult to find him to get on the first step. This is called the basic step. And the other one is where he make him go from one to the next. That is called the induction step. And so, I don't know the word induction. What you could say is induce here. You induce, he induces the program, or the robot induces that if he's on a 1 step, then what to do to get to the next step. try to think of it that way. That's the word induction step. And this is where the real induction happens, okay? So if you think of this as a program, this would be actually a loop, right? So this, in all these loops that we have seen, especially the four loops, are basically inductions, where you go from one counter to the next one, and you keep carrying out a task, okay? So, so that's the idea, but how does it work in a proof? And to do this, I'm going to already start with a particular example. I like to do this right away on an example, because otherwise it's too abstract. But first of all, it is mathematical truths that we want to discuss here. So we want to prove something. So there is a statement, okay? You might say this is no statement here, right? That's true. And this is not a proof, this is a program. But so what the proof would really be say is, if I design my robot to do this, my robot knows these two things, then, and this is now the theorem, then my robot can go up any number of steps you want. That's the theorem. So the statement would be, so this is the setup. So the statement that I now make about my robot is the statement, robot can climb up to step n, where n could be any number, 5, 700, 2000, 5 trillion. Of course, some things 5 trillion might not be feasible, right? Because that is a little bit the magic of induction, is that even huge numbers which cannot be carried out actually, because we don't have the time or the space, the universe will be gone by the time the robot has climbed up a billion steps. Not a billion steps, but there are much huger numbers. But yet, that's the claim that I make. So remember, so n, this n now looks like an, I must admit that my n looks even like an m. So this is how I write my n, right? So this is a statement about the natural number n. So we always write these predicates. It's a predicate, right? N is the variable. I write these predicates as Pn. Okay? And so the statement is Pn. Robot can climb up to step n. Okay? Now, remember that when you make a statement like that with a variable in it, you will, let's think back at the beginning of the course. Predicates, can they have truth value? No, not really. It's only propositions have truth value. A predicate involves a variable. So implicit here, of course, is for all n. We have seen this, that very often one makes a statement without actually saying that we mean for all n this is the case. So keep that in mind, that very often we will not say the for all n, but it is there. Okay? So, but I'm not going to prove this one by induction. You could try to figure it out, but I'm going to do a real mathematical thing. My statement, so for now, therefore, the Pn's in this lecture will always be a statement about the natural numbers. What kind of statement? So here's an example of a statement. If you take the sum of the first n numbers, and let me just write it that way, 1 plus 2 plus 3 plus dot 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 plus n, then that is equal to n times n plus 1 divided by 2. Now this is a formula that we actually saw, and it was in the table. This was from the table in, I forget now which section, that was chapter 3 I think. So look up this table that gave us this formula. Okay, by the way, at that time we had this notation here, and we would write this sum more compactly with this sigma notation. Okay, I going from 1 to n, it mimics a little bit more the for all loop, right? And we keep adding the i's. I'm just saying that because in the book one often uses those symbols, but I'm very happy that you use the somehow long form. It's more telling, it's more understandable. So I'm going to always use this type of forms rather than these summation formulas. So this is a claim, right? So I'm claiming that if you take the sum of the first n numbers, then this is equal to this, is given by this function, by this formula. Okay? So there's a left-hand side and right-hand side. Keep that in mind. And the statement depends on the variable n, and again, as I said, this means that we have to prove this for all n. So how does this now relate to this basic step in induction step? The basic step was to get the guy going, to start off. In other words, the very first thing that needs to be done. So the very first thing that we would consider here is, of course, n equals 1. So for us, so remember, there are two things. Proof by induction. Proof by induction has two ingredients. That is the basic step, and that is the showing that the very first value for n, which in this case is 1, but it doesn't always have to be 1. We will see examples where very often we actually start from 0, and sometimes you have to start even from 3 or 5 or something like that. Okay? So the basic step is, so this 1 is the first applicable value. Let me say that. In this thing, it's clear that it cannot be 0, right? Because we write here 1 plus 2 plus dot n. So the smallest you can go is write just n here, of course, then there's no 2 and 3. Okay? We understand this kind of convention, right? So this is the basic step is always about the first applicable value, the first value. And what we need to do is, well, prove this, P1. So in the basic step, you just do a direct proof. Let me direct proof, perhaps direct proof in a more general sense. We just prove that, P1. Now, what does P1 say? Let's see. So we have to figure out what does P1 actually state. Well, on the left-hand side, it means it is 1 plus 2 plus 3, plus n plus 1. Well, that means we just said that on the left-hand side, we will only write 1. So the left-hand side, that is 1. What is the right-hand side? Well, the right-hand side is this formally, right? And so we have to plug in 1 there. So this is 1 times 1 plus 1 divided by 2. Now, what is that? Well, that's clearly 1. I hope everybody sees this calculation, right? So we see left is equal to right, and that is how you prove equalities. Keep that in mind, because very often we're going to prove an equality. Not always. We'll prove other things as well, but just that is very common. What did I do? Okay, no, that was okay. No, I wanted to erase this. Really? What is it doing? Okay. But that's only the basic step. We have proven the theorem for n equals 1. Big whoopee. But that is basically telling now we are ready to do the induction step. And so this is the induction step now. And this is the thing that people get really confused by. What is the induction step? So before I even say it, I'm going to remind you of a mistake many people make when they write proofs is they have to show something and they're going to assume that it is true, and because they assume it's true, then they prove that it is true. Obviously that doesn't work, right? That is putting yourself up on your own shoestrings. You cannot do that, right? If you try to pull on your shoestrings to get you up, it doesn't work, right? So if you assume that something is true, yeah, of course you're going to prove that it is true, but that's not allowed. That's not how you prove things. And we're going to do something very, very much looking like it, but it is not that at all. Because what we're doing is we assume Pn. So we're going to assume the statement. Yeah, but Professor, you just said we cannot do that. Yes, but I'm not trying to prove Pn. We try to prove, in a other one-way, direct way, like the previous case, try to prove not Pn, but Pn plus 1. Remember, think of it as, here is the end step. You're standing here. Here your robot is standing here. Okay, I'm going to try my robot again. He's standing on this step, and now he has to go to the next one. So this is n plus 1. Okay, so how is he going to n plus 1? This is the task. If you can get to level n, Mr. Robot, what you need to do is now to get to level n plus 1. And can you do that? Yes, you couldn't do that because I made a program for you that tells you how to go up one step. This is what we want. If you want, this part here now proves that if he's standing on level n, then he can go to level n plus 1. So now, if we assume Pn, so if we assume that at level n, the statement is true, we have to now show that that also it is also true at level n plus 1. Okay, so it's not that we're assuming truth and then just use that truth to prove. It's not assuming, we're not assuming this and prove that, because that would be wrong. That pulling ourselves on a shoestring. What this is more is somebody else on a step higher is pulling us up on our shoestrings, and that will work. Okay, it has to be a bit good muscles and so, but he will get us up the next ladder. So how does this now work? Okay, this is what I'm saying how to do it, but how does it work? So as I said, there are two things. We assume Pn and we try to prove Pn plus 1. So let's see what is assuming Pn means. So Pn, we accept or assume, so let me write it one more time. So accepting, I'll write it this way, accepting Pn means that we agree that 1 plus 2 plus 3 plus ... plus n, that is equal to n times n plus 1 over 2. That is that. So this is let me make it in two colors. So assuming Pn, that is this formula. Okay, so that is this thing here. What is the other one? Oh, perhaps I should do this a bit bigger, right? So what is this one? Try to prove Pn plus 1. Let me, sorry, it looks a bit weird the way that I was doing this, so let me get rid of this. So let me make it in the bigger here. So assume Pn, okay? So this is what we assume. Oh, let me do, sorry, okay, since I'm playing with colors, let me therefore, I should use green for things that we know, okay? So assume Pn. So green means this is what we know, or rather this one here, perhaps, let me not, it is the green one, that's the formula that we can use. What is it that we need to prove? Let me do that in orange. It's not, we don't know it yet, so it's not red, it's not wrong, but we don't know it yet. So what is that? What does Pn plus 1 say? So we need to show what? So how do you get the statement Pn plus 1? What is that? Well, that means that in this whole big statement, you replace, every time you see an n, you replace that with n plus 1. Okay? That is what it means to, what the difference between Pn and Pn plus 1 is that in Pn plus 1, it's not the value n, but the value n plus 1. So let's look at where is an n. There's an n here, there's an n there, there's an n there. So let's write down what we need to show. You have to show that 1 plus 2 plus 3 plus ... plus n plus 1, right? That n, that first n, this n here I am replacing now. And now here, this would be what? This would become n plus 1 times n plus 1 over 2. Sorry, I should have brought it a little bit on the same spot, but I hope you see it here, right? Replace n by n plus 1, and this n by n plus 1. So of course, n plus 1 plus n plus 1, that is n plus 2. So I'm going to actually write it that way, right? Otherwise, you might say, what weird thing are you writing there now? Okay, so this is what I need to prove. Now, this is what we need to prove. So it's a question mark, whereas here it was an okay. We knew that check mark. We knew it was true. Here we have to prove it. That's the difference between knowing and needing to prove. Okay. So that's the setup. Okay, so let me now make this. So this is what we need to prove. But then we need to still do this. This is not the end of the story, because this needs to be verified. We need to get rid of this question mark. Is this true? And how we do this? Well, we work again as we did in the basis case, the basic case, or basis case, or base case. We analyze what the left-hand side is, we compare with the right-hand side. If they're equal, then we are happy. Okay, sorry, this was equal to 1. That was the one that was here. Okay, so what is the left-hand side? Left-hand side. That is one of what? The left-hand side of the orange guy, right? The one that we need to verify. Okay, 1 plus 2 plus 3 plus ... And the last one is an n plus 1. Just question, so n plus 1, let me put it like that, right? What was the one just before that? N, right? So because what is the difference between this formula or this expression and this expression? Well, there's just one more term, namely this term, right? So n plus 1 here is the next value for n. So the previous one was n. So in other words, if I analyze this sum here, I see that up to here, but not the last one, this is something that I know. This is the same as that. And I know, check mark, that this is equal to that. So we can replace this expression by that expression. Why? Because we know it's true. Check mark, we have accepted it. We are accepting that Pn is true. Okay, that's the weird, like perhaps seems like good, how to say that, that we are cyclic, like look like a cyclic argument, but it isn't. Okay, that's the strength of this whole thing. So let's replace this. So we're replacing the green thing by the other side. We know this is true. So here again, yeah, that's perhaps not legible. So let me do it in green here. So I replace the green line by the other green line that is equal to it. Okay, and what is left then? Well, what is left is plus n plus 1. The one start is left. Now, where we going? We're trying to get the right-hand side, and for one thing, this is on a common. This is on one denominator, and this is not. So let's start with putting this on a common denominator. Okay. So what is this? That would be n. Let's perhaps expand this also. N times n plus 1. That is n squared plus n over 2 plus 2n plus 2 over 2. You agree with me? Okay. So that is n squared plus 3n plus 2 over 2. That's just basic algebra. Okay, that's the left-hand side. I'm not going to do more with it now. Perhaps I need to, but for the moment, I'm going to look now at my right-hand side. Okay, what is n plus 1, n plus 2? So n plus 1 times n plus 2 divided by 2. Oh, okay, so before I go on, this, what I denoted here with this green arrow is replacing this by that. That was using this truth that we accepted, that we assumed. And that has a name. We call this the induction hypothesis. Right? A hypothesis is something that you assume to be true, and then you have to get your conclusion from it, right? The induction hypothesis, and we will always abbreviate this IH. So, and in a proof, you always, there's a standard thing to do to denote it or mark it, and so I want you to do that too, is always write the place where you're actually using the induction hypothesis. In other words, where you're using this green truth. And this is the place where we use it. And very often we only use it at one place. So now you might be tempted to say, okay, now let's try to write this in this form and then do something with it. No. That's not how it often works. Often we just apply it at one point, and now everything else should fall in place. We should not use this anymore. We should just need to work this out. Well, you'll see what happens. Well, we have to expand, right? FOIL it. That is n squared plus 2n plus n plus 2 over 2, which is n squared. And then like terms plus 3n plus 2 over 2. And you see the magic. It's exactly the left-hand side is equal to right-hand side. So the formulas match up. And that's the proof by induction. Okay? So that is how it works, and we can do now very nice things. So another one, I'll do another one here. That Pn, I'm always going to call it Pn, but of course there are always different Pns. Pn is the statement that the sum of the first n odd numbers is n squared. That sounds weird, right? The sum of the first n odd numbers is n squared. So what you could do often, so let's see, let's try to prove this. Okay, so prove by induction. So we have to do the basic step, and we have to do the induction step. What is the basic step? The basic step says P1. What is the first sum of the first one odd number, well, that is just 1, right? So the left-hand side is 1. And what is n squared? So n squared is now take the value also 1. So 1 is equal to 1. So what I mean to say here, perhaps, the first n odd numbers when n is 1, that is that one. And n squared when n is 1 is this one. And of course these are equal. So you see the basic step is very easy. Now, sometimes, so I'm going to put this between parentheses, meaning this is not necessary, but sometimes you need to see what is going on here before you can go on. So let's actually even verify this. Is this true for... oh, I'm saying it, sorry, what I said is not right. No, what is, I'm saying it wrong. No, I say it right. No, it's right, okay. So let's see what happens if n is 2. So, curiosity. This is not proof, this is just curiosity. If n is 2, what do we have? On the left-hand side, so this thing becomes 1 plus, the next odd number is 3, right? Okay. What is the right-hand side? Well, 2 squared, 4. Yeah, that's true. Okay, I'm really curious now. N is 3. Perhaps that's just accident, okay? So 1 plus 3, what's the next odd number? 5. This is equal to, well, I'll be damned. That's equal to 9, which is indeed 3 squared. So we start believing it, right? So this is what I'm saying between parentheses. This is not part of the proof, but you sometimes need to convince yourself before you actually can prove something. I mean, never prove something that you don't believe is true, okay? We have seen in politics many of these examples with elections being won or lost and trying to prove, nonetheless, knowing very well that you actually lost, trying to prove that you won. That's not something one should do. That a normal, sane person doesn't do things like that. Okay, so here's the induction step now. So let's write down what the induction says. So it's 2 parts. We assume Pn, so that always tell yourself, right? The basic step is 1 part, it's just the original statement. The least value for which the statement can make sense, prove that. And the induction step has 2 components. That is an assumption and something that you then have to derive from that assumption. And the assumption, which is what we call the induction hypothesis, right? Remember, induction hypothesis. So assume Pn, that means assume that 1 plus 3 plus 5 plus ... plus. Now, we have to write down what is the nth odd number. We need a formula for that, okay? So the first odd number is 1. The second odd number is, what is that? Well, that is 2 times 2 minus 1. 5 is 2 times 3 minus 1. 7 is 2 times 4 minus 1. So it seems that the nth odd number is 2n minus 1. Now this needs a little bit of thinking. I agree, not always these things are so easy, but my claim is that this formula tells me what the nth odd number is. That's just verify again to make sure that we don't have the right thing, because you might say, oh, is it not 2n plus 2 plus 1, professor, instead of 2n minus 1? Well, let's see. I'm going to do like, these are 1, 2, 3, 4, 5, 6, okay, the 6th one. So according to this formula, the 6th one will be 2 times 6 minus 1, 12 minus 1. Oh, okay, so yeah, right. So I have the right formula. This is the 6th odd number is given by that formula. So that is correct. Okay, let me get that out of the way now. And what is the claim is that this is equal to n squared. Okay, and it's an induction hypothesis. We assume that this is true. Okay, to show, we need to prove that the same is true if we replace n by n plus 1 in this expression, in this formula. So this is need to show. Let's write down what that means. Well, let me call it the actual. So, okay, so what is this? That 1 plus 3 plus 5 plus ... plus. Now replace n by n plus 1. That's what it means. Okay, 2 times n plus 1 minus 1. Okay, let me put this. I'm putting this between parentheses to indicate that this is one quantity. I consider this as the nth term, right? This is the first term, second term, third term. This is the nth term. And so now this is therefore the n plus 1 term. Okay, equals, I replace n by n plus 1, so here I get n plus 1 square. And this is question mark, make it orange, because we don't know yet. Okay, so now we have to prove. So, proof. So because we have to show this, right? So there's an extra, inside the induction proof is if you want a second proof here. I didn't formulate it like this here, but this is what we did here, right? So and very often when it comes to equalities, you look at the left-hand side. So what's the left-hand side here? So we get 1 plus 3 plus 5 plus... So which left-hand side am I talking about? The one I need to prove, not this one. The one I need to prove, okay. Okay, plus, dot, 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 plus. So I'm going to write this a bit nicer. So plus, that is 2n plus 2 minus 1, so 2n plus 1. Now, and we've seen this also because, look, I have to relate this formula somehow to this formula. So what is the connection? Well, the connection between this and that is that this has just one more term. So let's add, that means that the previous term was just this 2n minus 1, right? So we have 2n minus 1 here. Okay, that is the left-hand side. Now, and that is the beauty of this thing, is that most of this is already indeed that thing that I know. Well, I'm assuming it, so I can replace this. This is exactly what I referred to as the induction hypothesis. So this is the induction hypothesis, and I can place this quantity by the right-hand side here, namely by n squared. So we replace this by n squared, and then plus what remains is this guy, right? So plus 2n plus 1. Okay, but what is the right-hand side? I mean, it's so obvious that I don't need to work it out anymore. N plus 1 squared by the double product formula, that is n squared plus 2n plus 1. So again, they are equal. Cool, no? Okay. So I want to do perhaps one more. Let's do this one. Also in the tables we have seen formulas like this. If you do 1 plus 2 squared, 2 to the power 1, this would be 2 to the power 0 then. So okay, now let me write it first this way. Plus 2 cubed plus 2 to the n, that is equal to 2 to the n plus 1 minus 1. So this is again the statement I make. So let me call it Pn, and we need to prove this. Okay, so the proof by induction, I'm going to go a little bit faster now, okay? What is the basic step? What is the smallest n that this applies to? Well, actually, not n equals 1, because n equals 1, what would that do? If n is 1, then this formula, P1, would say 1 plus 2 to the power 1 is equal to 2 to the power 2 minus 1. Now, that is true, of course. Yes, because the formula is going to be true. So this is true, but it's not the basic step, because there is even a smaller step. Here, the basic step is P0. I can look at this as a statement about the natural numbers, including 0, because this one is just 2 to the power 0, and we already used it, that is 2 to the power 1. So P0, on the left-hand side, we get just 1, 2 to the power 0, all the way up to 2 to the power 0, so that's it. Is that equal to, question mark, 2 to the power, now I plug in 0 in here, 2 to the power 1 minus 1. No, yes, that is 1, so yes, that is true. Basic steps are often extremely easy to prove. So it's a bonus. And so if you don't understand really how it works, do at least the basic step, because it's, first of all, it's clear what to do and it's easy. So you can get at least some partial credit for the problem. Okay, now what is the induction step? The induction step is we assume Pn and to show Pn plus 1. So what is Pn? That is the statement that n1 plus 2 plus dot 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 plus 2 to the n is equal to 2 to the n plus 1 minus 1. So again, I make this green. This is something we know, so we accept it. What is the thing that we need to prove is 1 plus 2 plus 2 squared plus dot 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 all the way up to one higher power, right? So we in replacing n by n plus 1 here, and here it will become n plus 2, right? is equal to, so we don't know, question mark, 2 to the n plus 2 minus 1. Okay, so the n plus 2 comes from replacing this n by n plus 1 and then add another 1 to it. Okay. So the question here again is this true? Okay, but we know, hopefully see how this works, right? Left hand side, if I unravel the left hand side, that a lot of it is actually something that I have in the green part, namely, what's the term just before this one here? Well, 2 to the n, right? It's just one less. And then the next one will be 2n plus 1. That's the left hand side. So this one again, up to here, that's something I know, and I know it's equal to, so here by the induction hypothesis. So here comes the deduction hypothesis. This is the induction hypothesis, the green thing. We know that this is equal to 2 to the n plus 1 minus 1. And now I'm going to add 2 to the n plus 1 to it, right? This is this part here that I'm copying here. This green part, let me perhaps make it green here. This here comes from this formula, equality. So replace this by that. This I just copy. Okay, now let's combine this. There's a 2 to the n plus 1 and another 2 to the n plus 1. So there are 2 times 2 to the n plus 1 minus 1. But what is 2 times 2 to the n plus 1? That is 2 to the power 1 times 2 to the power n plus 1. So you add exponents, right? That is 2 to the power n plus 2 minus 1. And here we are. This is actually the right hand side. I don't even have to analyze the right hand side. It's exactly what I needed to show. Okay, so this is how proofs by induction work. Now it doesn't always have to be, I'm going to do one more and hope that my pen doesn't run out of juice. I'm going to do one more, is proof Pn is the statement that n is less than 2 to the power n. This is something we often say that we have talked about this, right? The polynomial growth or linear growth is much smaller than exponential growth, and so let's verify this here. And so, what is P1? The basic step. We'll go a little faster now. Pn would be, the question is 1 less than 2 to the power 1. Yes, of course it is. Okay, so P1 is very easy. So what is so this is the basic step. So what is the induction step? Well, assume Pn to show Pn plus 1. Do this, take the time to write this out. Don't just write out what Pn is. Just write it down this way that you don't make mistakes. Okay, assume that this is true. That's Pn. So again, this is something we can assume. What is Pn plus 1? Well, replace n by n plus 1. So n plus 1, is this less than, question mark, we don't know yet, here we know, then 2 to the n plus 1. Okay, so this is what we need to show. So this is what we're after. Now, this is not a little bit less left and right hand side. So, and very often, if you cannot do it from a left and right hand side, what you do is you start from the induction hypothesis. So the induction hypothesis tells me what I can assume, I write it in green, that n is less than 2 to the n. That is something I am allowed to assume. This is not me pulling myself up on my own strings, because it's this one I'm after, not this one. This one I know already, so I'm not interested in that. This is the one I'm interested in. Now I have to get somehow to this form. Now you see that under this n here, there's an n here, and here's an n plus 1. So I have to somehow make this into an n plus 1. And I want to relate this to this. And that is the trickery. This is something that you can only do by trying many different proofs and see each proof has its own way of solving this. Professor, why can you tell us how to do this? It should tell us how to make proofs. Well, if I would tell you that, then I'm out of a job, because my job as a researcher, not my teaching job, but my research job, is to come up with proofs. And if it's easy to make proofs, if there is a recipe to make proofs, yeah, then what am I doing? I'm just a cook. No, I'm not a cook. I'm a scientist that tries to find proofs. So it's not clear how each proof has to be approached a little bit in its own way. But once you see a particular problem, problems of similar nature are then also proved similarly. That's luckily often what happens. So what I'm going to do therefore is I'm adding 1 to both sides. Add 1. That is a valid operation, and it doesn't change the the inequality. Okay. Now that takes care of the left-hand side of my inequality, but not the right-hand side. So I would actually want to replace this 2n plus 1 by this 2 to the power n plus 1. Is that equal? No, that's not equal, right? Be careful. You cannot just bring the 1 up and then say, oh, I'm done. No, that does not work here. But note that 1 is less than or equal to 2 to the power n, right? That is clear, no? Whatever power of 2 you take, it's at least 1. I mean, even the 0th power, which is 1, and then the first power is 2, and then 4, and so on. So this is clear. So I can make this even a weaker inequality by replacing this one by this bigger quantity. This makes it remember, what this means is that this quantity is not as big as this quantity. So I'm putting here a bigger quantity, namely 2n. I'm just copying this one. It's this one I replace. So let me perhaps make that clear by making it in a blue. So I'm using this here. This is the truth that I'm using, nothing to do with the assumption. This is another mathematical truth. So I'm replacing this one by 2 to the n. Okay. Now, what is this? That is 2 times 2 to the n, which is of course 2 to the n plus 1. And there we are. See, just this little trick. It is a trick, right? You have to come up with this little thing here. But once you see it, you get the solution almost for free, I would say. Okay, I'm going to assign... I think I'm going to stop here because we're going to do one more session. The next session, I'm going to do a little bit more involved proofs, which some of them I still expect you to know how to do. And then at the second part of the lecture, I am actually going to do some more fun stuff that you can do with it, with induction. Because induction is also can lead to very nice things, actually, fun results. Now, before I end, I just very quickly, I want to give you a wrong proof, a wrong use of induction. And here's the thing I want to prove. So Pn is a statement that this is only for n at least 2. Okay, so sometimes we make the statement for all n, including 0. Sometimes in the first ones were n, for all n at least 1. Now I'm saying for all n at least 2. If a meadow, you see there's not even mathematics here. If a meadow has 1 white horse, if a meadow with n horses has 1 white horse, then all horses are white. So I'm claiming that if you put 1 white horse in the meadow, they're all white. That's nonsense, right? I don't know if you ever drove to a countryside where there are horses. You can see white horses are rare, but sometimes you see a white horse and it's running with 2 black horses. So that is definitely not the case. But here's my proof. For n equal, I said for n at least 2. I don't know why I said that. I mean for n at least 1. Right, okay, so that was kind of 0 horses. We don't talk about 0 horses. So I'm not even going to say that. Sorry, I don't know why I said that. Oh, sorry. So the base case, so basic step, or base case, P1. If a meadow with 1 horse has 1 horse in it, then all horses are white. Yeah, that clearly is true, because there's only 1 horse. Okay, great. So now, induction step. Pn. So assume Pn to show Pn plus 1. It's getting out of juice here. So what is Pn plus 1? So let's go immediately to this Pn plus 1. So here is my meadow, and we have n plus 1 horses. And I know one of them is white. So let's make this the white horse. So one of them is that's not going to be visible, right? So my white horses will look a little bit gray. So this is my white horse. Okay. So what I'm going to do now is I'm saying, okay, so there are n plus 1 horses. One of is white. Let's take one that I don't know yet. This one is and it's not a white horse. I see the white horse. I'm telling the other horse that I see there, say, hey, come aside here, and I close off the meadow, I put it aside, and here are the other ones. So how many are there left in this side? N, right? There's N horses now. Now, what is this? So if I put here a little fence, and this one horse is sitting here, and the N horse is sitting here, now we have a meadow with N horses, one of which is white. Assume Pn. We know that Pn is true. We're assuming the Pn, and that includes, therefore, all horses are white in this meadow. Okay, so this means now in not one of them, but all of them. So here we are, they're all white. Now, what about the last horse? Okay, sure. What I do now is I say, okay, I'm going to do a second argument. Let's get away with the fence. Go back with your white brothers. And now taking one of the white guys, here, one of the white guys, separate him. And now we have a meadow with a lot of white horses and one horse that I don't know yet, by the same induction hypothesis. So this was the induction hypothesis, made all these white. Now, looking at this meadow, so I'm using now, and I said, most of the time we don't, but this time I used the induction hypothesis twice. So the induction hypothesis applied to this meadow of also N horses, because I separated this one white horse, okay, makes it true that, well, there are many white horses, but at least one, therefore, by the statement, by the assumption, by the induction hypothesis, this is a white horse too, and they're all white. Professor, this cannot be true. What are you telling me? You made a mistake in your argument. Yes, of course, I made a mistake, but where? Well, I think you shouldn't use induction. Induction is not right. No, induction is right. What is the mistake I make? Let's look at, so analyze this at level 2. The very first next step. Let's do the same proof that I did here. So we have two horses, one of them which is white. Okay, that's the assumption. Okay, so this is, I'm assuming P2. N is, so at level, I said 10. So I should say it this way. So what I want to do is, so assume P1, well, actually we showed P1, but okay, to show P2. This is the case here for n equals 1. So this is the induction step for n equals 1, right? This is, if you put 1 here, so assume P1, well, we actually proved it, and then to show P2. Okay, so what the argument was, I'm following my previous argument. I separated one of the horses which I didn't know the color of yet, and put all the others in the other meadow. So this was separate in this guy. And then I said, okay, so this is now a meadow with n horses in it, right? One less, because I removed one. And therefore, it contains a white horse, and therefore they're all white. Yes, sure, that's true. So far, no mistake I made. And then then the weird thing comes. Then I said, okay, now, the second part. Remember what did I do in the second part? I said, let's take one of the white horses, of these many white horses that we had, right? At this point, we didn't know that this was white yet. So we removed the fence. I said, let's take one of the white horses that we have, remove it, and look at the remaining meadow. And we said, oh, there are a lot of white horses in there, so this remaining guy also is white. But look at this. This meadow has a horse in it, but it's not, well, as far as we know, not a white horse. There was only one white horse at this point. When n is 2, so in the case of n is 2, there is only two horses, and so the argument falsely claimed that in this part there is now a white horse, and therefore everything is white. No, there isn't a white horse, so that was where it was wrong. Now, I'm giving you this, and I'm sure you cannot appreciate this because you don't still understand how induction works. Now, don't get frustrated about this. I'm a mathematician. I was trained mathematics. I always had a great interest in mathematics, and the first time I saw induction, I almost run screaming away. It's weird. It's something you have to get used to. And in the beginning, you feel like this cannot be. This is strange. You're doing things that are not allowed. And then you see this kind of false proof, so it completely throws you off. This is normal. It takes a while to actually grasp this kind of higher level thinking. This is really that sets us apart somehow from how to say animals, or even lesser less intellectually inclined people, they will absolutely go berserk on this, but you guys are a bit mathematically trained, and although you feel like this is magic and you don't understand it, when you do more of these proofs and you do the homeworks and so, you gradually will get a little bit of the hang of it, and hopefully in Discrete Math 2, I hope everybody's going to take it, you will get even more confident with it and see that this actually makes a lot of sense. And in fact, if you ever know, if you ever become a programmer or something like that, you might want to do these things or use these things, because it is really something about for loops. That is how the idea of for loops works. And we will not talk about it, but very often part of computer science is not just making the programs, but showing that the programs are actually doing what they claim to do. And that one, you need induction. Because you have to, each time you use a for loop, you almost always going to show by induction that the for loop is doing what it's supposed to do. I'm not going to do this. This is 5.3. You can read this if you're interested in it. But next time I'm just going to continue with some more examples. All right.